In this video, you're going to learn about multiplexers, how they work, and how to use them to design logic circuits. A multiplexer is a combinational circuit that has 2 to the n data inputs and n select inputs. It also has one output. So for example, we can have a 2 to 1 multiplexer. We can have a 4 to 1 multiplexer. And we can have also an 8 to 1 multiplexer. In this case, we have 2 to the 1, right? We have 2 to the 2 and 2 to the 3. In this case, we have one select input, select. We have two select inputs or signals. And in this case, we have 3 select signals, okay? And so the general diagram, for example, for a 2 to 1 is like this. So we have 0 and a 1, and we have a select input. And so the idea is that depending on the select input, if we have the select input is a 0, then whatever value we have here is going to get passed to the output, and so on. And for example, for the 4 to 1, we have two select inputs, S1 and S2. For example, we have our output F, 1, 2, 3, 4, for data input. So we have 0, W1, W2, W3. And these W's can be 0 or 1, right? We don't know the value, we just know that that value is going to get passed. So 0, 0, 0, 1, 1, 0, 1, 1. So if we have our select inputs 1, 1, and 1, so that means that the value of these is going to be passed to the output. Okay. So how we design for a multiplexer? So for example, we're going to do the 2 to 1 multiplexer. So we're going to put a truth table. We're going to start with a truth table as 1, W0, and then W1, for example. And so we're going to have 0, 0, 0, 0, 0, 1. Of the values, possible values. And so if S1 is a 0, it chooses the W0 values. If S1 is a 1, it chooses the W1 values. So in all the top part, it's just going to choose 0, 0, and 1, 1. Bottom part is going to choose the values of W1, so 0, 1, 0, 1. Okay, and then we can do the K-map for these, or we can do just the mean terms and Boolean algebra, but it will end up something like this. So K-map will be I have S1, W0, and W1. I have 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. I would recircle this one, probably just this and this. Okay, so for the green one, so we have S1, not W0, and the red one we have S1, W1, right? So final function will be F equal S1 not. And so we draw the diagram for that. We're going to have a so W0 I'm going to put here, and then I'm going to put a not. It's going to be S1 and W1. So that will be what's inside the multiplexer block diagram. Okay. So if we wanted to look at the functionality truth table, we would see that we have S1 and F. So if the select value is a 0, it chooses the value of W0. And we don't know if it's a 0 or a 1. If it's S select value is equal to a 1, it chooses whatever value is the W1. In the case of the 401 multiplexer, we have 4 data inputs and 2 select inputs. So depending on the value of the select inputs, that's the value that we're going to pass to the output. So if we have a 0, 0, we pass the value of W0. If we have a 1, 1, we pass the value of W1, W3, I'm sorry. So we also can form the 4-to-1 multiplexer using the 2-to-1 multiplexers. So the key here is to choose the select values appropriately. Okay, so for example, the S2, that's our least significant value, and we're gonna put it in this level. The S1, which is our most significant value select, we're gonna put it at here. So for example, if we have a 0, for S1, it's gonna select the top part of the truth table, for example, which is going to be this. I'm just gonna put it as green, for example. All of this is gonna be corresponding to this top multiplexer, okay, and so on. So now, what are the steps to synthesize logic circuits using the multiplexer? So first, we're gonna determine the number of select input variables. That's gonna depend if we're using a 2-to-1 or a 4-to-1. I'm just gonna put 4-to-1 multiplexer or an 8-to-1 multiplexer. Or we can also have the 16-to-1 and so on. So the number of select input variable is going to be depending on which multiplexer we're going to be using. We're going to choose the select variables. We're going to start with the truth table. From that, we're going to choose the select variables. We usually choose the most significant bit variables, and then we're going to split the table. Then we're gonna check the remaining variables, the least significant bit variables. We're gonna compare those to our output of the truth table, and we're going to, then after that, we're going to draw a diagram for the whole circuit. So let's do some examples. So first I need to determine the number of select input variables. So since in this case, we're gonna have a 4-to-1 multiplexer, we're gonna have 4 data inputs, 1, 2, 3, 4. I need to be able to count from 0 to 3. 0, 1, 2, 3. How many variables do I need in binary to count to do that? So I basically need 2. So because I'm going from 0, 0, 0, 1, 1, 0, and 1, 1. So using the 4-to-1, I need 2 select input variables. And so we're starting from a given truth table from a problem. So given a truth table, or if we have a written problem, we can, from those directions, we can have a truth table created from the verbal instructions. Second step is to choose the select input variables, okay, and then divide. So since I have A, B, C as my input of the truth table, I'm going to select the most significant bits for my select. So I just put them right here. I draw the diagram, I draw the block diagram, and I put A, B as my select. I then split the table vertically, okay? That's the first division. Then the second splitting of the table, that comes from having four inputs. So if I need to have 4 inputs, I need to divide in 4. So 1, 2, 3, 4. The next step is to compare. So what are we going to compare? We're going to compare the remaining variables. Which is the remaining variable from these 3? So A and B I use for select. The remaining one is this C, okay? So this C is my remaining one. And so I'm going to compare this column with this column, with the column F. And so if I compare this column, and also I'm going to be comparing by each of the blocks. So I have 4, and I have this division. So I'm going to be looking at these two. How do this compare with these two? And by that I mean, does F depend on C? So if C is 0, F is 0. If C is 1, F is what? F is also 0. So in this case, so does F depend on C? So for example, in the top row, we have that if C is 0, F is 0. If C is 1, F is still 0. So it doesn't depend at all on the C. It's just always going to be a 0, right? What about this next one? So if C is 0, F is 0. If C is 1, F is 1. So that's just completely is F is equal to the C, right? It's just following whatever the F is following, whatever the C is. What about this other block, the next block right here? So similar, right? F is following the value of the C. If C is a 0, also F is also a 0. And then what about the last one? The last one, I have F is always a 1, right? C is a 0, F is a 1. C is a 1, F is also a 1. So we have a 1. So just remember that this F, where this came from. So the A, B, and C, they just come from all the possible values that three binary variables can have. A, B, C can go from 0, 0, 0 to 1, 1, 1. Those are my values. Then F is the output from my problem statement. F is the output from the truth table that is given, and so on. So all of this table is given. We're just finding out this. Okay, so that's what I mean by comparing. So we have 0, C, C, and 1. The last step is that we're going to draw the diagram. So once I have 0, C, C, and 1, we're going to do the diagram. We have our multiplexer, we have A and B, and then so for my first block, I'm just going to put a 0, because whenever I choose A, B, 0, F is always 0. Then a C, because whenever I choose A and B, 0, 1, I'm looking at these two, right? So it's just going to be C. Whenever I choose a 1, 0, I'm going to look at this. I'm just going to put a C. And then the 1, 1 is always going to be a 1. So that's how we design a circuit, okay? Instead of having AND gates, OR gates, etc., we can just use a multiplexer. I'm going to do another example. So now we can use a 16-to-1 multiplexer. We have 16 rows, so that wouldn't be that useful. We can use an 8-to-1 or we can use a 4-to-1. We're going to start with the 8-to-1. So how we determine the number of select. Remember, we have to count from 0 to 7 because we have 8 data inputs. How many variables, binary variables, do I need to count from 0 to 7? I need 3, right? So 3 select, 3 select. And so I'm going to be dividing my table, which is the next step. I'm going to be selecting the 3, right? I'm going to be selecting 3, and I'm going to be dividing into 8 pieces also, right? So how do I do that? Like that. So I'm selecting the 3 most significant bits, A, B, and C. That's going to be my select. And then I do a vertical line on that. And then since I'm using an 8-to-1, so I need to divide my table in 8. So that's a 1, 2, 3, and so on, all the way to 8. That's how we divide it. Now, we're going to compare the remaining variables. Compare the remaining variable, which is in this case, which one? The D. So we're going to compare the D with the F. Okay, so for example, in this case, what is this? Is it 0? Is it 1, the F all the time? Is it equal to D all the time? Is equal to D? Or is equal to D naught? So we have those possible options. Always 0, always 1, equal to D, equal to D naught. You can see this one is equal to D naught because when D is 0, F is a 1, right? What about the next one? This one. Same case, right? D naught. What about this case? Always 0, always 1, D or D naught. So in this case, we have a 0, right? What about the next one? We have a 1. Next one, we have a 1. This one, we have a D naught. This one, we have a D. And this one, we have a 0. Okay, so we're comparing with the remaining one. So the last step is just to do the drawing. So we have A, B, C, and then we have D naught, 0, 1, 1, D naught, D, and 0. In this case, you would only need, for example, if you're building this in the lab, you only need a multiplexer. You connect directly A, B, C to these select inputs, and then the D to a NOT gate, and that's it, right? So maybe I'll do this one. Let me redraw. There's actually D, variable D. What about if that instead of using an 8 to 1, we use a 4 to 1 multiplexer? So remember, for a 4 to 1 multiplexer, I have two select inputs, right? Two select inputs, and I'm going to have 4 data. So we choose the most significant bits, and then we split table in 4, right? So that's going to be this right here, because I'm selecting A and B as my select inputs. Then I need to split in 4. So 0, I'm going to be selecting here. You can kind of see the selection, the division is AB 0, 0. So in these top 4 values, right? What about the next one? A and B is 0, 1. The next one, A and B is 1, 0. And so that's how you divide. So what would be then my each of these section equal to? So I need to compare the remaining variables. I need to compare the remaining variables, in this case, the C and the D. I need to compare with the F, okay? For that, we're gonna be using also, if C or D, we're gonna be using a C and a D, or we can do smaller truth tables that we can find the mean terms, okay? I can even do K-maps for each of these individual ones. So for example, if I do a K-map for the first one, if it's not very obvious, then we can do a K-map. So for example, we have C, we have D, 0, 1, 0, 1. So we have a 1, 0, 1, 0. If I circle that, that is just a D naught, right? So in this case, we have D naught. What about the next one? We can do another K-map for that one. C and D, we have 0, 0, 1, 1. What would that be? Just a C, right? If I circle that one, that's just a C. What about this next one? 1, 1, 1, 0. So for that one, I kind of need this, and I need this one, right? So this one is D naught, and then this one is C naught. And so in this case, we have D naught plus C naught. And then we can also have, we could also have this one, right? Is which is A, B, not, right? A, B, I'm sorry, C, D, C, D, which is C not plus D not. What about this last one? The last one, that is just this mean term, right? So we have a C not D. And so we can do individual K-maps if it's not too obvious. Sometimes we have just the mean term, sometimes we have all ones, sometimes we have all zeros, sometimes we could have um, a, the C's or the D's and so on. But once we have that, we can draw it. Actually, let's just rewrite this one. We had this one was C not D. This one was what? C naught plus D naught. This one was equal to C, and this one was D naught. So if we draw that, we end up with this circuit. So 0, 0, 0, 1, 1, 0, 1, 1. We have A and B. And so remember we have the D naught, we had the C, we have the C, D naught, just a NAND gate, C, D naught, and then we had the C naught, and we had the D. So C naught D. So much simpler than having a bigger circuit.